Hello everybody. Now we will continue the system software and operating system unit. Here we were solving some problems there. In the paging problem, that is the fourth problem, the A subdivision, number of pages required for the given address space. It was not quite visible in the video, so I thought of explaining again. So I'll just read out the question here. Consider machine with 16 GB main memory and 32-bit virtual address space with a page size of 4 KB. Frame size and page size is same. So find the number of pages required for the given virtual address space. So that is the question, and here is the answer. Here we found out the main memory. Main memory value is given as size is 16 GB. So 16 GB means write it in form of 2 power 4 and 2 power 30 as it is in GB, convert it as bits. So 2 power 4 into, as in GB is 2 power 30 bits, so 2 power 4 into 2 power 30, which means 2 power 34. So number of bits used in the main memory is 34 bits. So here the page size is 4 KB, and then 4 KB means in the write it as in form of bits means you write 2 square into 2 power 10 as it is a KB, so 2 power 10. So we get, that means it is comes 2 power 12. So 12 bits for the page size. So page size and here the page size and frame size, that is offset is the page size. So both are having 12 bits. So page size and the frame size are the same. Okay, so both having 12 bits. So we found out that page size and we have found out the size. Here the question is what are the number of pages in the logical address space. Here the page number we have found out that it is given as 32 bits. 32 bits is given. Here we found out the main memory. They were given 16 GB. Here they given 32 bits for the logical address space. So here we found out that the page offset is 12 means remaining is 20. So remaining was 20. Remaining was 20. So here the number of bits in the for the page number is 20. So the number of pages here, number of bits used is 20 means number of pages is 2 per 20. Okay. So next we will do the last sum. The last sum is consider the following three processes with the length of CPU burst time given in milliseconds. Say a process 1, process 2, process 3, 3 processes, arrival time 0, 1, 2 and burst time is 849. What is the average waiting time for these processes if they are scheduled using preemptive shortest job first scheduling algorithm? Okay, let us solve this sum. First we'll draw the table for the sum. See, that is given process. I'll write in short. Okay, arrival time, burst time is BT. Okay, so next what we'll write, we'll write the completion time, then turnaround time, and then the waiting time. Okay, so what are the processes? That is P1, P2 and P3. Arrival time 0, 1 and 2. Burst time is 8, 4 and 9. So you have to find out the completion time. So completion time we have to draw the timeline, how will it comes to draw the chart. So here we know that in time 0 what arrives, P1 arrives. So P1 is it is a preemptive shortest path algorithm. What is this? It is a preemptive shortest job first scheduling algorithm. So here first P1 first gets the CPU, so it starts at time 0. So it will do for 1 second only, 1 millisecond. Okay, because it is preemptive. So next at time 1 what arrives, P2 arrives. So P2 arrives, it sees that burst time is 4 only. So what it just, so P2 will be schedule. So P2 is scheduled in the CPU. So P2 is scheduled at a time 1, and then it does 2 seconds. Okay, if you take 1 second means it is done for 2 milliseconds. It does the job, but afterwards in 2 seconds what arrives? P3 arrives. So when P3 arrives, it finds that the CPU finds that here P2 has a burst time of 4, but P3 has a burst time of 9, and P1 has a burst time of 8. So time to find that all the three processes are there, but among them which will choose? It will choose only the lowest burst time, the one which is the it has the shortest job. So this is the lowest burst time. So it will choose P2 only. So P2 will continue. So from 1 till how much ever. So first P1 has got 1 second. So reduce burst time reduces by 1. Then P2 will reduce till it is for 4 milliseconds. So 1 plus 4 is 5. So till the 5 milliseconds P2 will work function. Next we find that P1 has 7 burst time and P3 has 9 burst time. So it will choose the process 1 because it has lowest. So P1. So P1 it will run for 7 milliseconds. So P1 will run for 7 milliseconds. So 7 plus 5 is 12. Next P3. P3 is only one remaining. So P3 will run for 9, has 9 burst time of 9. So 12 plus 9 is 21. So P3 completes. So now I write the completion time. So what is the completion time of P1? P1 is completed in 12 milliseconds. P1 is completed. Then P2 completion time is 5. P3 the completion time is 21. Okay, so when you know the completion time, next we have to write the turnaround time and waiting time. So what is the turnaround time? Turnaround time is completion time minus arrival time. So turnaround time, the formula is completion time minus arrival time. What is waiting time? Waiting time is turnaround time minus burst time. So this is the two formulas which is in doing these CPU scheduling algorithms. So we'll apply this one. So completion time minus arrival time. So 12 minus 0, that is 12. 5 minus 1, that is 4. 21 minus 2, that is 19. So what is waiting time? Waiting time is turnaround time minus burst time. So 12 minus 8, that is 4. Then 4 minus 4, which is 0. 19 minus 9 is 10. So here you can write as you have all three schedules, so you can write the burst time, can reduce the burst time. So here we have to, now what is the given? We are asking the average waiting time for this process. So waiting time average only we are asking. So find out the average. So find the total, that is 14. So the average waiting time is 14 by 3. So it is 14 by 3. 3 4s are 12. So 12 and remainder 2. And then 20, 26, 36, 18. So 4.66. So average waiting time is 4.66 milliseconds. So this is the answer. Thank you for watching. So next we'll see the next unit problems. Okay, I hope this was useful to you. Please write your feedback in the comment section. Thank you.